Hello all. In this video we will discuss big theta notation. First we will start with what is the drawback of big O and big omega notations. So let's see this. If we have got a function 7n plus 5, we want to prove that it is big O of n square. Now certainly if some algorithm step count happens to be 7n plus 5, we know what is the time complexity. It is order of n, because what we do, we ignore the constant, we ignore the coefficient. So we'll say that the time complexity is order of n. So we'll never ever say that 7n plus 5 is order of n square. But our definition of big O notation proves that mathematically. So f of n is 7n plus 5 and g of n is n square. So 7n plus 5 is less than or equal to some constant c into n square? Certainly yes. So when c should be as small as possible, let's take c as 1. And if you choose n naught as 8, then starting from 8 and onwards, this equation will always be true. If you substitute n as 8, 8 into 7, 56, 57, 56 plus 5, 61, 61 less than or equal to 64. 8 square is 64. And then starting from 8, 9, 10 and onwards, this equation is always true. So although in practice we will never say that 7n plus 5 is order of n square, our big O notation can prove it, that 7n plus 5 is big O of n square. So it places an upper bound, but it doesn't tell you how good the bound is, right? So that's the trouble, right? So 7n plus 5 is less than or equal to 1 into n square for all n greater than or equal to 8. So that is the drawback of big O. Let's see the drawback of big omega notation. If you have 7n minus 4 and you want to prove that it is big omega of 1. Now 7n minus 4, according to what we know, we can ignore the constant, we can ignore the coefficient, and 7n minus 4 would always be order of n. But we will never say that it is a constant time complexity algorithm, because it has got an instant dependent term in it, that is n. But mathematically a big omega notation can prove it. So that's the drawback of big omega notation, that we can prove that 7n minus 4 is big omega of 1 constant time complexity, which is wrong. So f of n is 7n minus 4, g of n is 1 constant, right? You want to prove that 7n minus 4 is greater than or equal to c into 1. If you choose c as 1, then of course starting from n naught as 1, the equation holds. 7n minus 4 would always be greater than or equal to 1 into 1 for all n greater than or equal to 1. So although in practice we will never say that 7n minus 4 is a constant time complexity algorithm and 7n minus 4 is order of 1, a big omega notation allows us to prove it, because it only places the lower bound and it doesn't tell you how good the bound is. So the theta notation is more precise than big O and big omega notation. Okay, so big theta notation places both the bounds, as you can see, upper bound as well as lower bound. So here we need to choose two real constants, c dash and c double dash, and we want to prove that c dash into g of n is less than or equal to f of n, less than or equal to c double dash into g of n for every integer n greater than or equal to n naught. N naught can be anything greater than or equal to 1. Here C dash plays the role of C in big omega notation, and C double dash plays the role of C, constant C in big O notation. Okay, so C dash plays the role of C in big omega, and C double dash plays the role of constant C in big O notation. So suppose we want to prove that 7n plus 5 is big theta of n. So f of n is 7n plus 5, g of n is n. So we want to prove that c dash into n is less than or equal to 7n plus 5 less than or equal to c double dash into n. So here if you choose c dash as 7 and c double dash as 8 and starting from n naught as 5, this equation would always hold. 7n is less than or equal to 7n plus 5 is less than or equal to 8n for all n greater than or equal to 5. If you substitute the values of n as 5, 6, 7, 8, whatever, this will always hold. We can prove that 7n plus 5 is big theta of n. What we are doing, we are placing both the bounds. Starting from a certain value of n naught, f of n would always lie in between c dash into g of n and c double dash into g of n. F of n would never go below c dash into g of n, and f of n would never exceed c double dash into g of n. It would always lie in between. So what we are doing, we are placing an upper bound as well as a lower bound over here. Both the bounds are placed over here in case of big theta notation. The theta notation is more precise than both the big O and big omega notation. Suppose we want to prove that 7n plus 5 is big theta of n square. Can we prove that? No, because finding c double dash will be possible, but finding c dash is not possible. Similarly, you cannot even prove that 7n minus 4 is big theta of 1. Okay, because again here finding c dash would be possible, but c double dash won't be possible. So the problem is big O notation is placing an upper bound, but it doesn't tell you how good the bound is, right? Big omega notation places a lower bound, but it doesn't tell you how good the bound is. Here big theta notation places both the bounds, right? So you cannot prove something which is wrong. We will never say that 7n plus 5 is order of n square, and big theta notation never allow you to do it mathematically as well. Similarly, 7n minus 4 can never be order of 1, and big theta notation will not allow you to prove that as well. Okay, so considering other two notations, big O and big omega, big theta notation is more accurate. So henceforth, while denoting time complexities, we will use big theta notation. Okay. In the next video, we will see a master method for solving recurrence relations and finding out the time complexity. We will see several examples for that. Thank you.